So we're going to be doing 5.5 and 5.6 today. So 5.5 is on triple integrals in cylindrical and spherical. Sorry. You can see that there is a lot of information that you should pay attention to. I may have forgotten to upload them, so I'll do that tonight too. I plan on working after class a little bit today, so I appreciate the reminder. So I'll make sure I do that. I do have all the PDFs saved, I just didn't upload any of them. So we are going to do this first example. You can probably bet that it has something to do with this theorem. So it says here, we want to evaluate the triple integral ZR sine theta R dr d theta dz, where the cylindrical box B is the following. Okay, so it says, as stated in Fubini's theorem, we can write the triple integral as the iterated integral. So the evaluation of the iterated integral is straightforward. Each variable in the integral is independent of the others. So we can integrate each variable separately and multiply the results together. So that's going to make this problem that you initially might be like, oh, that's gross, a lot better. So this is what it would look like. So we're going to go from 0 to 2 pi, and then from 0 to 2, and then from 0 to 4. It's going to be, ZR sine theta R dz dr d theta. Try to squeeze that in for you. That's dz dr d theta. So now we're going to split everything apart. So we'll have 0 to 2 pi sine theta d theta. And then we're going to have 0 to 2 r squared dr. And then 0 to 4 z dz. So that'll give us a negative cosine theta from 0 to 2 pi. And then r cubed divided by 3, 0 to 2. And then z squared divided by 2, 0 to 4. And if you plug in and figure out all those evaluations, you're going to end up with an answer of 64 over 3. Okay. All right. Hopefully that was a nice one to get us started. So this next one is saying setting up a triple integral in cylindrical coordinates over a general region. Consider the region E inside the right circular cylinder with the equation r equal to 2 sine theta bounded below by the r theta plane and bounded above by the sphere with radius 4 centered at the origin. Set up a triple integral over the region with the function f of r theta z in the cylindrical coordinates. So they give you everything there that you'll need to set up the problem. Now first you want to identify that the equation for the sphere is going to be r squared plus z squared equals 16. We can see that the limits for z are from 0 to the square root of 16 minus r squared. Then the limits for r are from 0 to 2 sine theta. And then finally the limits for theta are from 0 to pi. So that region would look like this. And then if we do the integrals, it's going to be over that region. And it'll be from 0 to 2 pi, 0 to 2 sine theta, and 0 to the square root of 16 minus r squared. Gonna have and then I think they just wanted us to set it up. I don't think they wanted us to go any further than that. Doesn't look like it anyway, so. Yeah, set up the triple integral. So you didn't have to solve it, just have to set it up. All right. Nice and easy one. That would probably get a lot of people because we don't like to read in life. I also was falling under the trap thinking we had to keep going. All right, so hopefully we can get both of these parts on here. To set up a triple integral in 2 ways, let E be the region bounded below by the cone z equal to the square root of x squared plus y squared, and above by the paraboloid z equal to 2 minus x squared minus y squared. Set up a triple integral in cylindrical coordinates to find the volume of the region using the following orders of integration. So we want to first do dz, dr, d theta, and then for b, we want to do dr, dz, d theta. If we need an extra slide, I'll put it in, but hopefully we'll be all right. So the first thing you need to pick up on is that the cone is a radius of 1. Where it meets the paraboloid. Since z is equal to 2 minus x squared minus y squared equals 2 minus r squared, and z equals the square root of x squared plus y squared equals r. Assuming that r is a non-negative, then we would have 2 minus r squared equals r. And then if we solve, we'd have r squared plus r minus 2 equal to r plus 2 r 1 equal to 0. We're probably going to need another slide. And then since r is greater than or equal to 0, then we have r equal to 1. So that means that z equals 1. So the intersection of these two surfaces is a circle of radius 1 in the plane z equals 1. So circle the cone is the lower bound for z and the paraboloid is the upper bound. The projection of the region onto the xy plane is the circle of radius 1 centered at the origin. Thus, we can describe the region as the following. So we would have E bar theta z 0 to pi 0 1 and then r z 2 minus r squared. So this is all the setup you need to do A. And then once you do all that, then you can actually do the part A, which is going to be the volume 0 to 2 pi, 0 to 1, r to 2 minus r squared, r dz, dr, d theta. And again, that's all you have to do. You just needed to find the volume. That's probably why I thought I could do this all on one slide, but do part B over here. All right, so we can also write the cone surface as r equals z, and the paraboloid as r squared equals 2 minus z. The lower bound for r is 0, but the upper bound is sometimes the cone and other times it is the paraboloid. The plane z equals 1 divides the region into two regions. Then the region can be described as, so we basically will have a union for our region. And it's union with all right, so now the integral for the volume would have to be a summation. So it's going to look like all right. So I think what they're trying to do here with some of these where we don't have an actual quote unquote answer is they're just trying to do a lot of those, or like a lot of like set up theoretical ones, so that you guys can get the sense of kind of like if they gave you a similar problem, then you would know what to do with it in a non-theoretical setting. All right, so this one again wants us to do the triple integral in two ways. We want to let E be the region bounded by below by r theta plane and above by x squared plus y squared plus z squared equals 4, and are the sides by the cylinder x squared plus y squared equals 1. So then they give you a visual. Set up a triple integral in cylindrical coordinates to find the volume of the region using the following orders of integration, and in each case find the volume and check the answers are the same. Okay, so it looks like I gave us two sides for this, so that's a good thing. Okay. All right, so for part A, all right, so we want to note that the equation for the sphere is x squared plus y squared plus z squared equals 4. Or you could say r squared plus z squared equals 4. And the equation for the cylinder is, this is for the sphere. And then for the cylinder, we would have x squared plus y squared equals 1, or r squared equals 1. So then that would give us the following region. Sorry. I absolutely hate coughing, and I hate people that cough, and now I just hate myself. So being sick sucks. I think we're doing pretty decent on time now. Yeah. All right, so now we can do the volume. The volume of E is going to be 0 to pi, 0 to 1, 0 to the square root or minus r squared. R dz dr d theta. All right, then Okay, cubic units. So a pretty weird, disgusting answer, but that's what it is. So we'll accept it. All right, now we're going to work on part B. Okay. So since the sphere was that r squared plus z squared equals 4 and the cylinder was r squared equals 1, then we would have 1. So hopefully you guys don't need me to rewrite this, but what that tells us is 1 plus z squared equals 4, then z squared equals 3. So then we're going to have two regions since the sphere and cylinder intersect at the intersection point. Okay. So you're going to have two. You're going to have E sub 1 So what we should notice is that we should get the same answer. Oops. Don't know why I did that at all. All right. So you see that we have the same answer here. Two different ways to get it, but same nonetheless. Less. Sorry. All right. As long as you guys have that written down, I believe there are some notes. And there are. Go ahead and try to take down what you would like to take down, those of you that take handwritten notes. So we're going to be switching now from cylindrical to spherical. And we're going to go through some problems. Okay. Right? Okay. So we're evaluating a triple integral in spherical coordinates, so we want to evaluate the following. So you can see where it starts. I'm just going to go ahead and pick up from it. So that's the first step. You would rewrite this. I'm not rewriting it. Try to save us a little bit of space. Okay. So then if you guys are going to do your work, get the following. And then you end up with an answer of 2 pi over 3. Again, much like everything else, you can see that everything's starting to build, so you're not getting all of the pieces. Oh, that's nicely. All right. So kind of a similar image as before. We're using conversion formulas from rectangular coordinates to spherical. We would have the cone would be z equals the square root. Well, that's what they give you. So we're just going to do the conversion. So that would be or oh, yeah, again, they wanted us to rewrite it. I just don't have the space to do that. I don't know why they keep having us to. Okay. So that's telling us that the volume is going to be 0 to 2 pi, 0 pi over 6, and 0 to 2. Okay, and again, that's all they wanted. They didn't care if you figured it out for real, just the setup. Okay. All right. All right. So again, it looks like I was smart and gave us 2 slides. Wish I would have done that for that one, so we weren't without a picture, but so it says let E be the region bounded below by the cone and above by the sphere. Set up a triple integral in spherical coordinates and find the volume of the region using the following orders of integration. So for the sphere, we know that we have x squared plus y squared plus z squared equals z. Right? And then for the cone, sorry to go Christmas colors. We have z equal to the square root of x squared plus y squared. Okay. Okay. That was a lot. All right. So then we can finally do the volume for part A. Okay. And again, they didn't care for you to find the actual answer. They just wanted that theoretical. All right. So that's part A. Part B. Okay. We want to consider this plane. So from part A. They're not going to make us do it again, thank goodness. And that's not a 6. It's one of those Greek letters that I can't seem to remember which one's which. And so I understand if you guys have a hard time with them. Okay. All right, so then the curve of, what is that, rho cosine phi? Meets the line at the point so to change the order of integration, we're going to need 2 pieces, right? These are the 2 pieces we're going to need. Okay? So that means, and we are going to do this the whole way through now, our volume so 0 to 2 pi square root of 2 over 2 1. Oh, I dropped my plus sign. All right, guys. All right, so in each case, the integration result, so maybe that's why they didn't give it to us in A, is going to be pi over 8. Okay. All right. Hopefully we will get done with 5.5 in the next 15-ish minutes and be able to start the next one. All right. So it says converting from rectangular coordinates to cylindrical coordinates, convert the following integral into cylindrical coordinates. So it doesn't look like we need to actually solve the answer. It looks like we just need to do the conversion. So we know that we will have, or I guess rather, the current ranges of the variables are -1 to 1, 0 to the square root of 1 minus y squared, and x squared plus y squared z to square root of x squared plus y squared. So the first two inequalities describe the right half of a circle with radius 1, and therefore the ranges for theta and r would be, let's not do Christmas. So then that tells us that the limits of z are going to be r squared r. So we would have negative 1 to 1. Oh, it's having us rewrite it. I'm just not down for that life. So the conversion will be negative pi over 2, pi over 2, 0 to 1, and r squared to r. R cosine theta, r sine theta, z, dz, dr, d theta. And that's the end of that. Okay. So this is the conversion they wanted. Right. Sorry if I'm going a little fast. I'm just trying to get us through to the next set of examples, next section. All right, so here we're doing the same thing except we're going to spherical. So we currently have 0 to y to 3, 0 to x. All right, so the first two ranges of variables describe a quarter disk in the first quadrant of the xy plane. Hence, the range for theta is 0 to pi over 2. Okay. First quad. All right, so the lower bound of z is the upper half of a cone, and the upper bound is the upper half of a sphere. So lower bound cone, upper bound sphere. So then that's going to get you and then that works to okay. And then for the ranges of that phi, maybe we need to find where the cone and sphere intersect to solve the equation. So kind of like a sidebar, you have to solve to find the one that looks like a 6. So r squared plus z squared equals 18. replace that with x squared plus y squared plus z squared equals 18. So that's going to be z squared plus z squared equals 18. So that's the same as saying 2z squared equals 18. So z squared equals 9. So then z is equal to 3. All right, so then if we plug that in, we're going to end up with 3 square root of 2 cosine rho equals 3. That's cosine 1 over the square root of 2, which would just mean that we would have pi over 4. I will find a way to squeeze this on here. So I'm not going to do the rewrite. You know, you would have to rewrite this. But they give it to you. So we're going to go and do the conversion. So it's going to be 0 to pi over 4, 0 to pi over 2, and 0 to 3 square root of 2. Oops. All right. Again, I apologize for going a little bit quicker. Okay, so this was about the chapter opening. Find the volume of the spherical planetarium, which is 5 stories tall and has a radius of approximately 50 feet using the following equation. So we're going to try to find this. What you will need to know is that we calculate the volume of a ball in the first octant, where x greater than 0, y greater than or equal to 0, and z greater than or equal to 0, using spherical coordinates. Then multiply the result by 8 for symmetry. Since we considered the region D as the first octant in the integral, the ranges of the variables would be okay, that means we would have our volume over the region D, dx, dy, dz equals 8 times 0 pi over 2, 0 to pi, 0 to pi over 2, rho squared sine theta. Okay, so then 8 pi over 2. All right, so we're going to have 8 pi over 2, r cubed over 3 times 1. We know what our r is, so it's going to be 4 pi, oops, 4 thirds pi r cubed. Well, that's just the volume anyway. So if we plug in our 50 feet, we would get approximately 523,600 feet cubed. Okay. All right. So now we need to find the volume of an ellipsoid. Find the volume of an ellipsoid. It gives you the volume, or the equation, sorry. So again, we're going to use symmetry and evaluate the volume of the ellipsoid using the spherical coordinates. As before, we used the first octant, which was, we found this information out. Okay. And then multiply the results by 8. In this case, the ranges of the variables are okay. Also, we need to change the rectangular to spherical coordinates in the following way. Okay. So then the volume of the ellipsoid and then we're going to pull out our 8ABC. All right, so then that gets us 8ABC pi over 2, 1/3, 1, which is just going to be 4/3 pi ABC. All right, that's all they wanted there. All right. And then we have one more example here. We're basically going to use what we just talked about. So it's directly related to the structure. And so what we just found in that previous problem was that the volume of an ellipsoid was 4/3 pi ABC. And in this case, we know You can write out ellipsoid here if you want. We know then that that's going to be 4/3 pi, 75, 80, and 90. Given this information, we would have approximately 226,000 feet cubed. All right, so from example 5.52, so still this section, we know that the volume of a sphere was, for this case, for the 50, remember, was 523,600 feet cubed. So therefore, the volume of the space inside the ellipsoid and outside the sphere, we're going to subtract the two. So volume of the hemispheric is going to be the ellipsoid minus the sphere. That's going to be the big one. Darn it. That's going to be 1,738,400 feet cubed, and that is your overall answer. Okay.